Lecture 9 covers sections 4.2.4 through 4.2.5. At the end of today's lecture, you should be able to determine the center of area of a body via a method of integration, as well as using tabulated values. We should also be able to determine the center of lines of a body. Now, for us to begin, we're going to talk about centroids of an area. If our body is of constant density, and our body is experiencing a constant body force, i.e. a constant gravitational field, and our body is also of constant thickness, where thickness is denoted as the variable t, we can reduce our center of volume equation to a center of area. That is, we can recall that our volume is equal to our mass divided by our density, and our volume is also equal to our thickness times our area. Thus, on a differential basis, we can say our differential volume is equal to our thickness times our differential area. And therefore, when we solve for our x location of our centroid, we'd have the integral of x dv per the integral of dv. If we make in our substitution for dv, we'd have the integral of xt dA per the integral of t dA. Thickness is a constant, so t comes outside our integrand, and we're left with the integral of x dA per a. Likewise, in the same directions, we have y bar being equal to 1 per a, the integral of y dA, and z bar being equal to 1 per a, the integral of z dA. To see this in application, let's locate the centroid, i.e. our x and y locations of our center of area, of a rectangle below. Our rectangle has a base b, and it's going to have a height h. Now, for us to determine y bar, we're going to take a moment about our x-axis. That is, mzx is going to be equal to the integral with respect to a of y dA. Now, our differential area is going to be our basal length, b, times the thickness of our differential area, dy. Thus, we'd have the integral from 0 to h of y, b, dy. Now, b is a constant. We can remove that from our integrand, and we'd be left with the integral of y dy, evaluated from 0 to h. Thus, we have b times y squared per 2, evaluated between 0 and h, which gives us bh squared per 2. Now, to calculate y bar, we are going to take this moment, mcx, and divide it by our total area. That is, we have bh squared per 2 divided by our area, which is our base times our height. And we are left with h per 2. Now, to determine our x location, we'll take a look at our moments about our y-axis. That is, m sub yz is going to be equal to integral with respect to area of x dA. Now, our differential area has a thickness dx and a height h. Therefore, we have an integral from 0 to b of x h dx. H is a constant, and we'll remove it from our integrand. Thus, we'd have the integral of x with respect to dx, which gives us h x squared per 2, evaluated between 0 and b. Thus, we have h b squared per 2. To calculate x bar, we're going to take m sub yz per the area. And this is equal to h b squared per 2 divided by our area, which is simply our base times our height. And we are left with b per 2. For common shapes, tables are provided. And I will click this hyperlink in a moment, but I suggest you do so now. Within this table, we have 2 and 3D centroids, as well as the areas of our object, which populate the denominator of our centroid equations. Now, it's very important to be aware of the axes in which x bar, y bar, and z bar are reported. For the location of our body with respect to our axis dictates x bar, y bar, and z bar. If we follow this link, we see for common shapes that we have our x bar location, our y bar location, and the area. We note for a rectangular area that we find our x bar to be our base per 2, our y bar to be our height per 2, and our area is bh. You can continue looking at the page for other general shapes in 2D and 3D.